Welcome to this presentation on the impact of climate change on coastal erosion and flooding. I'm Stephen Luger from PRDW, Port and Coastal Engineers, and this is a presentation for the South African Institute of Civil Engineering. So the aims of the presentation is to describe the impacts of climate change on coastal erosion and flooding, to present some of the methodologies that are used to quantify these impacts, and to discuss the implications and mitigation options. The approach will be some basic theory and terminology, some case studies, and some numerical modeling. You will see quite a few numerical model results scattered through this presentation, and the reasons are twofold. Firstly, it's tricky to observe or measure events that are happening in the future. And secondly, coastal modeling is something that I've specialized in. So the topics will be the climate change parameters, some case studies on overtopping, on mitigation by raising seawalls, on beach recession, and allowing us to draw some conclusions. So if we look at the climate change projections, our primary guidance is the IPCC, which is the Intergovernmental Panel for Climate Change. They've released their 6th assessment report last year, so it's very up to date. In order for them to assess the climate change, they've defined 5 emission scenarios, and those cover a range of possible anthropogenic or human drivers of climate change. And these are called shared socioeconomic pathways, SSPs. Just note that previously they were called RCPs, representative concentration pathways. And what these are about, one of obviously the biggest anthropogenic impacts is carbon dioxide emissions. And so this graph is showing the dates from 2015 to the end of the century, and it's showing the carbon dioxide emissions per year. And the red is SSP 5, 8.5. That is the worst of the 5 scenarios. And you can see what happens there. The CO2 releases go up and up and up by about 4 times higher than present, and they level off. In contrast, the SSP 1.9, that's the best case scenario. And in that case, carbon emissions drop down, and by mid-century, we've gone carbon neutral. And thereafter, we actually go carbon negative. And then there's the other scenarios in between. And each of these scenarios has an impact on, in this case, on the global surface temperatures. This is showing the increase in temperatures relative to the beginning of the last century. And you can see for the worst case, 8.5, it goes up to 5 degrees hotter. And for the best case, it's only about 1.5 degrees hotter. So the parameters we're interested in for coastal erosion and flooding are sea level rise, waves, storm surge, and tropical cyclones. So starting off with sea level rise. So if you want to have a sea level rise to use for a study, you have to make some decisions. And the kind of inputs needed is the first is to decide which of the shared socioeconomic pathways you want to use. Are you going to use 8.5, the most conservative one, or are you going to use a more intermediate scenario with a lower carbon dioxide emissions, if you think that's the most likely scenario going for the way that the scenarios are socio-political, technologically driven. And so you need to make a decision in that respect. The second thing is the scientific uncertainty. So the IPCC are typically presenting the 17th, the 50th, and the 83rd percentile. So that's shown over here. We're looking at sea level rise over the century. The red line would show the median projection for scenario 7, SSP 7. And then the shaded red would show the upper 83rd percentile down to the 17th percentile. So that would be like the scientific uncertainty around the median for that particular emission scenario. The third thing to look at is regional versus global. So Cape Town is around 8% higher sea level rise than the global average, so you need to take that into account. If you have rising or sinking of land, you need to take that into account. South Africa is generally relatively stable, but other places that were covered by ice sheets or where there's been oil and gas extraction, the land can be sinking, which obviously exacerbates the climate change. And then just watch out for the baseline dates. For instance, in this graph, they've used a baseline date of 1900. In this graph here, this is the sea level rise we're using for a recent study in Cape Town. So we're using a base date of 2019, and that's because we have leveled in tidal water level data around 2019. So we just need to look at what's happening from 2019 onwards. So this table is just showing some projected rises for Cape Town for the 8.5, so the West scenario, base date 2019, and then if we use the upper, which is the 83rd percentile uncertainty for scientific uncertainty, we get 0.26 in the middle of the century and about 1 meter at the end of the century. If we use the median projection, we get 0.2 and 0.76. So that's sea level rise. The second parameter is waves. I actually find that IPCC don't include wave projections in their assessment reports. However, there is a lot of research done on this, as mentioned there in those references, for example. And essentially, they're using the global climate models, the winds from the global climate models to force global wave models, and to see what's going to change. They're generally using a multi-model ensemble approach to, in other words, using a number of different models in order to get a range of outcomes, and it adds robustness to the process. So this plot is showing the change in the 100-year return period wave height over this century at the RPC 8.5. And what you can see around Africa, South Africa, the southern part, there's an increase in the extreme wave heights, and as you go up the west coast and up the east coast, there's a slight decrease in the wave heights. Other parts of the world, there's significant decreases of Madagascar, Mauritius, and then down in the Southern Ocean, there's a significant increase. So if we look at what's happening off Cape Town for the extreme wave heights, so that's the data in the plot here, you can see there's about a 2% increase to the middle of the century and about 4% to the end of the century. However, the mean wave heights, there's very little change. And it's essentially that the frontal systems are migrating southwards due to climate change, so they get further away from us. However, when they do hit us, because of increased temperature, increased winds, they are more extreme. The other thing we're showing here is wave direction, and there's a rotation in the wave direction. At the moment, the waves come from the southwest generally, and it's showing that they're going to rotate anti-clockwise, which means they're going to come more southerly, to about 2 degrees by the middle of the century and 4 degrees by the end of the century. And this can change the orientation of beaches. And on the west coast, for instance, the northern parts of coastal sediment cells will tend to accrete, and the southern parts of those cells will erode. So the third parameter we're going to look at is storm surge, just a quick definition. So that's the influence of meteorological impacts such as atmospheric pressure and wind that result in the sea level being above or below the predicted tide. So that's shown in this diagram. Here we have high tide. The storm surge is this distance here up to the red line. There is also shown in here is the wave setup. So in the surf zone, there's an additional elevation of the average water level, and then obviously the individual waves are causing wave run-up. And the sum of all these components will give you the total water level. If we want to predict the change in storm surge, we need to know the change in the pressure, because it's the inverse barometer effect. A low pressure increases the storm surge. It's also due to wind, so it's proportional to the square of the wind speed, and it's proportional to the fetch, and it's inversely proportional to the water depth. So we have projections of wind and pressure at Cape Town from CSIR, and based on that, we have about a 2.5% increase in storm surge by the middle of the century and 6% by the end of the century. The last parameter to look at was tropical cyclones, also called hurricanes or typhoons, depending on where in the world you are. You can see South Africa, it's not significantly impacted by tropical cyclones except northern KZN. But if you're working in Mozambique or Madagascar or Mauritius, then tropical cyclones are often the design case. This shows the IPCC projections, slightly dated actually, for the change in cyclone metrics over the century in the southern Indian Basin. So that's in this area over here, southern Indian Ocean. And what they're saying is that the cyclone frequency is going to decrease or stay the same over the century, but the intensity is going to increase by 10%, best estimate, or up to 15%. So it's similar to the waves, that the sort of average conditions may go down, but the extreme conditions get worse. Okay, so that's all the climate change parameters. If we now just as a study now, a case study, just to show how does climate change change the return period of extreme events. And I've done this exercise for storm surge at Cape Town because we do have good data here. We have 10, 20, 30, 40, 50. We have 50 odd years of water level measurements in Cape Town, courtesy of the SA hydrographer, and those are the measured water levels shown in red. If we look at the predicted tide in blue and then subtract them, we get the storm surge residual in green. But it's better to just look at this extreme event. That's a 2017 storm. So this is what it looked like. This is 1 week. So we have blue is the predicted tide. The red is what actually happened. So the water level that was measured, and green shows that there was actually a storm surge of about 1 meter above the predicted tide during that storm. And if we do an extreme value analysis of all the storm surge data for the 50 years, we can get the storm surge with different return periods. For instance, the 100-year storm surge is about 0.85 meters. So what I've done in this table is to calculate the store water level at Cape Town, and store water level is simply the addition of the tide plus the sea level rise plus the storm surge. And it's called store water level because it's actually just the water level in the absence of waves. So it's the water level that you would kind of measure inside a harbor where there aren't big waves. So it doesn't include wave run-up, it doesn't include wave setup, but it includes everything else. And we have the sea level rise that we discussed previously. I'm looking at 3 dates, 2022, 2040, 2070. So we have the sea level rise for those dates. We have the storm surge for those, for the different return periods. We have the storm surge of that extreme value analysis in the previous slide, and we can also adjust those for climate change from a few slides back. And we add all those together. And if we plot it over here, in 2022 is this green line. So we're plotting the store water level versus return period. And if we go to the orange line, that's how the water levels are going to go up in 2040, and the red is 2070. And if you then look at, say, a water level of plus 1.8 meters MSL, you can read off today that's going to happen once every 20 years. But if you go to the red line, you'll see that that's going to happen every year. So essentially it's saying that something that happens every 20 years today is going to happen every single year in 50 years' time. And the same with the 100-year event today becomes the 10-year event in 2070. Of course, the 100-year event in 2070 is something that we probably haven't experienced yet today. Just to emphasize, this is these sort of changes in return period are specific to Cape Town and to store water level, and they would be different for other parameters and at other locations. It depends very much on the slope of the extreme value analysis curve. Okay, so the second kind of case study is tropical cyclones. This is a coastal protection project in Mauritius. The client is GIB Mauritius and the Mauritius Ministry of Environment, Solid Waste Management and Climate Change. So Mauritius has a Ministry of Climate Change, which shows how important climate change is for an island like Mauritius. And the design conditions are tropical cyclones in this area, and we've done some modeling to look at the design conditions and look at the impact of climate change on wave overtopping and flooding. So Mauritius is over here. This is the island. The study site is on the east coast, shown over here. This is Grand Port, and the study site is actually right tucked away in this little bay here. So it's an extremely sheltered location. These are the coral reefs, and it's tucked away here. And this shows the proposed development. So this plot is showing the historical cyclone tracks at Mauritius over the last 35 years. You can see that this is Mauritius, this is Reunion, and you can see that there's been a lot of cyclone activity here. If we model the wind fields around each track, we can get over time the maximum wind speed as the cyclone went past. You can see this Dina had about over 50 meter per second wind speeds back in 2001. We can do an extreme value analysis of the wind, and we can read off, say, the 100-year wind speed of 46 meters per second. So that's under present day. We can then adjust that for the future, for instance, that 10% increase in intensity from IPCC. We've now modeled some cyclones, and this animation is showing the wind field as a cyclone arrives and passes over Mauritius, directly over Mauritius. So you can see those wind speeds, 46 meters per second, 100-year event in 2021. We obviously did lots of other different tracks and different intensities. This animation is showing the associated waves with those caused by those wind fields. Strong winds and long fetches leads to big waves. So you can see here 12-meter waves offshore. And then what we've done is this is just a detailed model, a nested model inside that other model, showing what happens to the waves actually as they reach the coastline and as they reach the coral reef. Just for context, so this is just the aerial photograph showing the reef, the coral reefs around the site, and the site is over here, which is over here. So you see the cyclones are arriving now. The waves are getting bigger, and up to 12 meters offshore, but they're completely getting broken by the reef, coral reef, and the waves inside the lagoons are much smaller. In fact, they're generally caused by the local wind waves, and the reef is effective in cutting off or breaking the swell. This is not a general. I don't think that this result cannot be generalized even in Mauritius. There are places where the reef is lower, it's much closer to the shore, there are gaps in it, and the reef does not provide nearly this amount of protection to the coastline as it does at this particular site. And then the last thing to look at is storm surge. So this is showing the water surface elevation as the cyclone comes past, and because there's a low pressure in the eye and there's onshore or strong winds, you're going to see a positive storm surge, so about 1.5 meters of storm surge inside the lagoon. The reason that there isn't a lot of storm surge offshore is that it's very deep there. Storm surge is inversely proportional to water depth. Okay, so the results of this is showing our nearshore design conditions. For 1 in 10 year event, we looked at present day and 2070, and if you look at the still water level, it's about the design still water level 1.7 meters NSL today, and goes up by about 0.7 meters in 2070, and that's due to sea level rise and due to increased storm surge because of the more intense cyclone. As we mentioned, the waves are very small at the site because it's protected by the reef, only 0.4, 0.5 meters. That's the swell coming over the reef, and this is the local wind waves generated inside the lagoon. However, because they have very short periods, they actually didn't produce a lot of overtopping compared to the swell. The other thing I just wanted to point out here, we did model obviously the 100-year condition as well, and if you look at the 100-year condition in 2021, today, in other words, you almost get the very similar result to what we saw at Cape Town, is that the 100-year condition today is about the 10-year condition in 2070. So although it's a completely different site and completely different set of hydrodynamics, in this case it's due to cyclones, tropical cyclones, we've got roughly that similar result. Okay, so if we look at the development here, there was damage to this coastline due to previous cyclones. So what they are doing is putting a rock revetment and also a nourishment or reclamation to extend the land and raise the land, protect it from flooding and erosion. And this is a cross section of the revetment. It's a rock revetment with a concrete cap, and then there's a promenade directly behind. And we're going to model now the overtopping over the structure due to the 1 in 10-year event in 2021 and 2070. So this is showing a model simulation of the wave transformation and then overtopping over revetment structure. At the top you can see 2021 and at the bottom 2070. So you can see the waves coming. This hatched area is showing the rock, and this would be the concrete crest of the breakwater. And what you can see that is in 2021 there's minimal overtopping during this 10-year event, whereas if you move to the bottom in 2070, the same 10-year event, you'll see that there's virtually every wave is now overtopping the concrete wave wall. So we can measure the overtopping rates for 2021. It's very small, 0.02 liters per second per meter. And looking at this hazard table, that shows us that the only hazard that is really triggering is some minor damage to fittings of buildings located directly behind the wall. However, in 2070, we have orders of magnitude more overtopping, and this is triggering a lot more hazards for pedestrians, hazards for vehicles, and structural damage to buildings. So I think these results show that how the climate change increases the overtopping and the impact. And we also saw again that in 2021, the 100-year event in 2021 at least will have similar impacts to the 10-year event in 2070. And the 100-year event in 2070 will cause severe impacts. The crest that we tested there is actually lower than the stillwater level for this event. So that may need to be raised in future. So that's where this adaptive design comes in, which means that we design the structure that we are able to raise it easily in future should this sea level rise that we're projecting here materialize. And it may be best not to raise it right now in case we have one of the better, less severe scenarios in the future. And so rather than sink the money now, wait and see which scenario is materializing and put in the adapter design based on what we see. Okay, so the next case study is just to show how effective it is to raise a seawall. The study site is Small Bay in Cape Town. So here's Cape Town. Small Bay is located here, which is over here next to Big Bay. And the study site is this piece of coastline. This is a perspective view of it. Shows a rocky coastline with a seawall, very low seawall, and a road directly behind the seawall and houses. There's also a sewer line running along the front. So we did the study for the city of Cape Town, and the roads and the buildings along here are already experiencing flooding and damage, and so that's the project is a redesign of the seawall, and one of the things was to look at the effectiveness of raising the seawall. You can see that under storm conditions, this is what it looks like. This house here is this house here, so this whole area here is completely underwater, and here's the waves hitting this seawall here. Okay, so we need to know the local design conditions. So the first thing is to look at the waves. So this is during this 2017, which is the worst storm we've actually had in Cape Town, or measured in Cape Town, is shown here as a spectral wave model. So the waves were about 12 meters offshore, very westerly direction, and showing the wave refraction. And this is just a detail near the site here. There's Robben Island. Here's the site, Small Bay, and we're extracting results at this location here, which is in about 23 meters of water depth, just offshore Small Bay. And this plot is showing we've got 42 years of data, and this is showing the peaks of all the storms over each decade. And we see that there's the 2017 storm, so that event there, that 5 meters is what you're seeing over here. And then the second biggest storm was in 2020, and the third biggest storm is 1984. So it is interesting and concerning at the same time that the two biggest storms have happened in the last 6 years, and time will tell, I think, whether that is a trend or whether that is randomness. We've done an extreme value analysis on these data over here. You can see, so you can read off the 100-year wave height at about 5 meters, and again, this is in 23 meters. Offshore, these wave heights would be about double. So there we have our wave climate. So this is a model simulation showing the wave transformation into the site at Small Bay. The site is located over here. This is a 3D phase resolving model, so it includes all the physical processes relevant, such as wave refraction, wave diffraction, wave breaking, reflection, run-up and overtopping. Okay, so this is now another animation just showing a detail of the study site. This is that area that we saw in the photograph at the beginning of this section, and this is showing the surface elevation, so you can see the waves overtopping the roadway here and flowing up between the buildings. So this is the surface elevation, and this is the water depth. So once the water has come over the wall, it's showing the water depth and the currents due to the wave overtopping. So this now is summarizing the maximum flood depths behind the wall. On the left-hand side is the existing seawall, and this is for the 100-year event in 2024. So you can see how far the flooding has inundated into the land between the buildings, and we're getting depths of more than 2 meters of flooding. And then on the right-hand side is exactly the same storm, but if we raised the wall by 1 meter. So you can see that it doesn't stop the flooding, but it causes significantly less flooding, less horizontal inundation, less depth. So to summarize, this is showing the different return periods and overtopping rates for the existing seawall and after we've raised it by 1 meter. And you can see that the overtopping is reduced by at least a factor of 4. And if you look at the hazards, associated hazards, 100-year event with existing wall would cause damage, predicted to cause damage to the road, and damage to vehicles or risk to vehicles. And when we raise the wall, we take away the risk to the road, and in some cases we take away the risk to vehicles as well. For instance, for the 1 year event, it's still safe for vehicles. So the conclusion is raising that wall was effective. The one thing it shows up is that once the water has overtopped the wall, it has to drain. It can cause ponding behind the wall and needs to drain back to sea. We did include gaps in the wall, but that does need attention. The challenge is to have a system that can drain the water back without making the flooding from the sea worse, back through the pipes, through the same drainage system. Another thing, or a comment really, is that I think this result also shows that you can't just simply, you won't be able to just simply raise the seawall to match sea level rise. And for instance, if the sea level rise is 1 meter, if you raise the wall by 1 meter, it doesn't mean you're going to be back to the same level of impact that you were before. It's very non-linear. The larger sea level is going to allow larger depth-limited waves at the toe of the structure, so you're probably going to get a more overtopping. So it is very site-specific what the mitigation should be, and you're also going to need clear design objectives. So one design objective may be to just keep the same level of risk as climate change progresses, or perhaps for more severe climate change, you're going to have to accept that the risk is going to increase. But you do need to have some kind of objective design basis for saying what do we need to design for, what level of risk are we going to accept in the future. Okay, so a lot of examples have been rocky coastlines or revetments. Now we're moving on to beaches. So this diagram is, the solid line is showing the kind of present day situation. So there's the initial sea level, and the solid line is showing the initial coastal profile. And the coastal profile tends to form an equilibrium profile known as a Dean profile, and it's just the way that it arranges itself to dissipate the wave energy. And typically a coarser or larger grain sizes lead to a steeper beach. Now, what happens when we have sea level rise? So this is the S here, and sea level rise is up to the dotted line. Because the profile is in equilibrium, it needs to also rise to make sure that the slope is maintained relative to the depth in order to dissipate the waves. So the seabed also has to rise up over here, as shown in this green. We need sand to deposit here. The question is, where does that sand come from? And the only sand area it can come from is actually by eroding the beach in this area here. So essentially what happens is that the profile goes up and it shifts landwards and causes beach erosion of the shoreline, or recession of the beach, in order for this volume that's eroded to match, to balance with the amount that's deposited here. And this is known as Bruin's rule, and it essentially says that the recession that we're going to get is going to be the sea level rise, the S, times the length of the profile, L, divided by the depth of closure, which is the depth beyond which the sand is no longer moved by the waves, plus the berm height. So what it's telling us is that the recession is proportional to the sea level rise, and it's inversely proportional to the beach slope. So a flat slope is going to result in more recession than a steep slope. So an important limitation of Bruin's rule is that it deals only with cross-shore erosion due to sea level rise. And if you want to know, there's a whole lot of other processes that will increase or decrease the coastline erosion on top of what's predicted by Bruin's rule. And things like availability of sand in the berm, storm erosion during short-term events, you'll get erosion of the upper profile. Gradients in longshore sediment transport could cause erosion or accretion of the shoreline, depending on the gradients, and the supply from rivers can also be changed. So there's a whole lot of other parameters or factors that could also cause shoreline erosion, and those need to all be accounted for. But as long as you do that, we're using Bruin's rule to look at the effect of sea level rise on beach erosion. So the last case study is to look at beach recession. It's at Strandfontein. Strandfontein is located, this is False Bay, Cape Point, Huncliffe. So it's in the western part of the northern beach of False Bay over here. And you can see it comprises this large circular tidal pool with rocks in this area and then sandy beaches to the east and the west. And this study is part of a framework study for the Strandfontein Coastal Node for the city of Cape Town. And as part of that framework study, we've looked at coastal erosion and flooding for two time frames, including climate change. So 2078, so that's 50 years after construction, and 2128, that's 100 years after construction. And we can use this as a case study for beach recession. So the first thing we have done is looked at the coastline trends from historical aerial and satellite imagery. We're using just the wetted line of the beach. So here you can see the wetted line. And those end up being very noisy because it depends on the tidal level, it depends on the waves and the wave run-up on the date that that photograph was taken. But nonetheless, if you plot that data, so this is dates from 1980 to 2000, until today, 2022, and at all the profiles that we analyzed, which are shown here, there's an overall erosional trend, and both on the east and the west side of the pool, and that trend is around 0.3 meters of erosion per year. If we now look at the historical sea level rise at Cape Town, it's about 3.5 millimeters per year. And if you can use the Brun rule to calculate the associated shoreline recession, and you also get very similar numbers, 0.3 to 0.4 meters per year. So it shows that the Brun rule is consistent with the observed recession, and that suggests that there are no additional processes leading to long-term recession at this site. So there's other things we talked about, like longshore gradients in the longshore sediment transport. It seems at this site those are not having a big impact. So we can basically apply the future sea level rise projections and the Brun rule to predict the future erosion. And that's what we've done. So this is some of the cogs. So you can see this is a beach profile at Strandfontein. We calculate the depth of closure. We know the wave climate, so we can calculate the depth of closure. We have the upper point of adjustment, which is the top of the berm or the dune. We can therefore calculate the typical slope of the profile and then apply the Brun adjustments. So the green is today, and the blue is 2078, and the magenta is 2128. Of course, it's much better to look at that in plan. So that's what we're showing here. So this is the present day. So we're using the blue is showing the sea basically up to the top of the run-up line, and then the yellow is the land. So plus 2 meters MSL is about the top of the wave run-up. So that shows beyond that, the yellow is showing the dry beach effectively. Okay, so what happens if we now apply the Brun rule to 2078? So we can see that the coastline has actually moved back about 44 meters due to the Brun rule, and it's moved back on the beach where the beaches are. So it's moved back to the east and the west of the pool. The pool, we're assuming, is maintained, so it's a hard structure. It may need to be strengthened, but the hard structures, which is the pool and the revetments directly on either side, would be maintained, but the beach is allowed to erode, and that's what's going to happen. We also have looked at the flood line and the erosion line due to in this case, the 10-year event, but we also looked at the 100-year event. So those lines are also shown on this image. So what happens now if we go forward another 50 years? And you can see another 50 meters odd of erosion. So a total of about 100 meters of erosion of the beach, both east and west. And this starts to have real implications. I mean, this is the NSRI building over here, completely underwater. This is Baden-Powell Drive over here, completely underwater. These roads, this car park. So you can see, because this is quite a flat beach, combined with the sea level rise, Bryn's rule shows significant erosion of the beach and recession of the beach. So just to show it again, we can go from today, 50 years time, and then 100 years time. Okay, so we've seen how the projected sea level rise results in recession of the soft part of the coastline, in other words, the beaches, by about 40 meters by 2078 and 100 meters by 2128. The mitigation options would be hard protection, such as seawalls or rock revetments, which would be able to hold the line in front of the beach, but they would inhibit the natural functioning of the beach, and you'd lose beach width and coastal amenity, and eventually there would be no beach, just a revetment. Could try other mitigation would be softer protection, such as dune stabilization, which would be a buffer against storm erosion and slow down the predicted long-term recession due to sea level rise. However, the only way to mitigate this long-term recession would be beach nourishment, which is an expensive option in this case. In contrast, the harder section of the coastline, like the tidal pool and the adjacent revetments, were able to hold the line as long as they are maintained, which would require raising the crests and enhancing the tow protection. Okay, so the overall conclusions of this presentation. I think these case studies have shown that climate change poses a serious risk to coastlines through beach erosion and flooding. These projections are evolving because there are changes to the carbon emission scenarios over time, and also due to increased scientific knowledge. The impacts are site-specific and require site-specific studies and clear design objectives in order to design mitigations. The existing hard coastlines will need to be raised and strengthened. The beaches are particularly vulnerable to recession by sea level rise. And given the limited resources, a city like Cape Town, I believe that strategic choices will need to be made about which sections of coastline will need to be, we want to maintain, which will need costly beach nourishment, dune construction and maintenance, groins to hold the particular beach that we're trying to maintain, to hold the sand on that beach. Other places, other parts of the soft coastline, we're going to have to harden, which means we're going to lose the beach amenity. And other places, we're just going to have to retreat, which is going to lead to the loss of the infrastructure that's there at the moment. So I think these are things that are going to have to be carefully considered strategically in the planning going forward. Okay, thank you very much for your attention.